Hello everyone and hello Bang Ida, and I'm Inyoman Widyasa Jayananda, J, and this is my explanation about the answers to my journal. So for the first one, construct the circuit and truth table of A latch that activates when it's slow using basic gates and converted using NOR gates. So this question asks us to create a active flow gate. So an active flow means that the circuit is high or active when the inputs are low or have the binary equivalent of zero. So as we can see, I've created one using AND and NOT gates. So this is basically the NAND, and I've created the equivalent, which uses two NOTs and an OR gate. Why is it like this? Because of the algebraic algebraic laws that you can use to create to form the same type of uh, equation, such as the NAND gate. Let me give you an example. So imagine if this is A and this input is B. So an AND gate is A times B, but now this is negated, so it becomes A prime plus B prime. And that's basically what happens down here on the equivalent. All right, so let me showcase you a bit. So an active flow is when the circuit goes active when the values are low. So here, for example, here if both inputs are high, then it goes low. If one of the inputs goes low, circuit becomes high because it bites the rule of the NAND gate. And this is the equivalent. The equivalent follows the same principle. If both of these are high, then this won't be activated. So the output that we are looking forward here is Q. Q is the main output that we will be focused on when we're working on flip-flops and latches. So we're moving on to the NOR gate form. The NOR gate form is pretty straightforward. You just create the equivalent to the NAND gates. So a NAND gate is formed by utilizing four NOR gates such as this. I'm currently using the narrow type here, therefore it's smaller. And it works the same. Wait, let me open it up. It works the same. Yeah, so both inputs are high, then value here goes low. And then one thing to remember is that I'm using some type of an SR latch. So the S for the active low is at the top, while the R is at the bottom. Set and reset. And this follows actually the same principle as what we've been taught before during class. Truth table for the three circuits. So when S is 0, R is 0, it's it's actually 1 and 1, but why is it not allowed? Because you actually don't want to set and reset at the same time. So that's basically not that allowed. See, right here, both inputs are 0, both inputs are 1, which is weird. Do you want to set or do you want to reset? Should be 1 at a time. Alright, moving on. Latch that activates when the value is high using basic gates and converted using NAND gates. So this is pretty straightforward and just like the previous one, but this time we switch things around. So this one uses OR and NOT gates, and the S and R switch around because it's one of the basic theories regarding latches. So I have an example here. Let's see the main one. So when S is 1, the output will be here, will be according to Q here. So Q will be 1. But if you try to, let's say, set and reset at the same time, you'll get nothing because you cannot really set and reset things at the same time. So when you move here, the reset, it will display the value here as 0, but the Q prime is 1. So when you put all these values to 0, it will store the values within the latch, or is essentially locking the values within this latch. Oh yeah, I didn't explain that earlier. So when this is 1 and this is 1, it locks the value here. Yeah, so that's basically the same. And NAND gates form. Since NOR gates and NAND gates have an inverse relationship with one another, so it makes sense that uh, to form the NOR gates form here, and NAND gates uses the exact same amount of gates that are needed. But the difference is within the truth table. So for the active high case here, uh, S and R both have value at 1. It will have a weird value, an ambiguity value. And the other ones is just the reverse of this truth table from 1A. So that's basically sums it up. And we'll be moving on. Construct a circuit of SR and D flip-flops using basic gates with their truth tables. So a flip-flop is essentially just a clock latch. So that means the latch has a controller and it's controlled by a clock. So this clock is like uh you know how clocks tick, right? Tick, 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 tick. It has a set interval when it's gonna tick. So in computers, clocks usually is like a sine. It's like a sine graph. So there's a time period where it goes up, and there's a time where it goes down. So that's basically the same for clocks in computers. Yeah. So here we have an SR flip-flop. This is using the active low because I'm using NAND gates in here. So I'm going to show it to you. And 2 SR right here. Right, so for example, first, When the clock is not ticking, it won't update anything because the clock here essentially controls everything around here. So when the clock is 0 and you try to change these, nothing will happen. But once the clock is ticking, for example right here, I control the ticking, the values would change. And this works basically just like the usual active flow. Right here. Now, where is this different? So it differs when the clock is stopped right here. So when the clock is 0, nothing will happen, right? It's only if the clock is turned again. All right, I made an error here. As you can see, this is why you can have the same values 1 and 1 for these active low. Right. So moving on. Truth table. Truth table. All right. Basically straightforward, almost the same as the previous one, but I've got to explain something. So X and X here means that it's like a don't care value in a Karnaugh map. So what does don't care means? So don't care is simply like this value can be either 0 or 1 depending on any kind of situation. But this is when the clock is 0. So when the clock is 0, nothing will happen. No matter how much inputs that you're gonna change, it's not gonna change anything within the circuit. This is why it saves, or it has a state of no change. All right, moving on. When S is 1, R is 1, it errors. As you can see from the previous one here, yeah, oscillation apparent. Moving on. 0, 0, when the clock is 1, it will be no change. So yeah, this is basically, yeah, gotta reset it. Gotta enable it. Simulation enabled. And there. There we go. It's not gonna change. And the other ones are the same. Just like the ones here. Moving on to D flip-flops. So yeah, a D flip-flop is simply just an SR flip-flop, but this one here. The inputs are fused into one wire, but the bottom wire or the reset state is uh is negated or inverted its value. Yeah, this is straightforward because it doesn't allow for these kinds of things to happen, or maybe like these will not happen. So let me show you a demonstration for a bit. Wait to zoom in. Right. Let me get the clock ticking. Yeah, so it just activates right away because none of the values here are gonna be 0 and 0. So it's either gonna be 0 here, 1 here, or 1 here, and 0 here. So we can just flick this up to set it between set and reset. Yeah, that's a simple explanation, really. So when the clock is stopped and set it down, yeah, it won't be able to change anything. So that's basically it. Make the circuit as shown below. Observe what happens to the output on the 7 segments. The clock keeps ticking. Why does this happen? Okay. So the question given us the task to construct this. And it's actually pretty simple. It consists of JK flip-flops, but you can make it using G flip-flops here. Because the power source here goes into both inputs of the JK flip-flops. So when both inputs are 1, it basically uses the toggle mechanism of the flip-flops. Let's run here. And as you can see, in the 7th segment, it starts counting up into the hexadecimal values. And because we're using 4 flip-flops here, it can store data up to 4 bits. That's why in here, C, D, E, and F, yeah. So it stores the values up to F, and it will repeat the cycle once all of these have been done. 8, 9, A, B, C, D, E, and F. Right. That's basically self-explanatory. If the clock keeps ticking, the output on the 7 segment will output hexadecimal values. Yeah, like counting forwards 0 to F infinitely until either the clock is removed or the fixed power source is removed from the circuit. Right, so yeah, actually. So simply the clock gives the power and to somewhat unlock the gate here and thus execute the JK flip-flop here. And the power source here basically does the toggling mechanism or the inversing of inputs within the flip-flops. So when toggle happens, the inputs will switch, right? You can see that it switches from the bottom wire to the top wire. That's basically what happens. Yeah. Toggles again, toggle again, toggle again. And it creates a delay between all of these flip-flops because it's gonna be explained soon. Yeah. So the clock continuously deliver positive and negative values on a set interval. Then the power unit is always inputting 1 to J flip within the circuit. I'm gonna add a bit here. Therefore, creating a fixed state of toggle. in JK flip-flop. In each JK flip-flop. Yeah. Moving on. Create a 1/6 divider. This is 1/6 frequency divider circuit using a flip-flop, maybe flip-flops, and create its truth table. Yeah, we can see here, I make it go from left to right. And it's basically the same concept as this, where there are four flip-flops connected to each other. And I'm still using JK here because this one uses JK, but you can also use T here. Oh, right. So it consists of the same exact stuff here, but the difference is here. We're gonna use this the output circles, or maybe you can use LED lights here to signify that there's an output here, and the output is 1. So that's basically what we're looking for. All right, so we're gonna measure this truth table here using clock cycles, but I'm gonna explain the circuit for you. So the circuit, and if I can find it, this is number 4. Basically the same principle as before. I'm gonna start the simulation here. Yeah, it counts up until why not? Until all of these are 1, 1, 1, and 1, which in binary is 15. So because this involves 4 JK flip-flops, it can store data up to 4 bits of data. Yeah. And the delay here is actually pretty simple. So let's reset it. When you first set the clock to pulse edge trigger positive, wait, not pulse, but edge trigger positive, it creates here, it activates the Q here. And when the clock is down, it's not going to do anything because this is positive edge triggered, or PT. And when the clock is up again, this will become 0. And the Q prime here, Q prime, is transferred here into a clock here, basically enabling this JK flip-flop to execute. So when this JK flip-flop execute, it's actually a delay by two clocks. Well, what I mean is, like, there's a delay with two clock up and downs. So that's a simple word I can come up with. So when this is up, this is once, down, this is twice, and up again. So when it's up, it counts as 1, down, and then up again. So there are 2 downs and 2 ups when this happens. When the Q prime is 1 here. So so it happens basically on when the clock is cycling twice. For simplicity, let me just show you or demonstrate. 1, 2, 1, 2, 1, 2, 1, 2, 2, 1, 2, 1. So each of these GK flip-flops and divide circuit by a half. That's why it takes each flip-flops takes half the time to gather the values from each one another. So there's a delay there. 1, 2, 1, 2, 1, 2, 1, 2. Okay. And therefore, this circuit actually divides by 1, 1 over 2, n for each flip-flop. Since we use 4 flip-flops here, this will be 1 over 2. So this will be 1 over 2 to the power of n. Since we have 4, then 1 over 2 to the power of 4. This thing is the power, not this one. Right, so from the truth table here, we can measure it using the clock cycle and using all these variables here, the output variables. So I created from 0 to 16 here because I actually want to prove when it goes back into the first clock cycle here, clock cycle 0. So during the first clock cycle, there's nothing happening, the clock is not on, and therefore all the outputs here are 0, 0, 0, 0. And when it's turned to 1, it starts counting up from here. So this outputs 1 here. And when the second clock cycle, it starts counting up in binary norms and so on and so forth right here. So I already explained here, the pattern is proven to repeat every 16 clock cycles. 16 clock cycles means 0 to 15, all right? Based on this truth table. Same case as the circuit for problem number 3, right here, where the binary equivalence of hexadecimal notations repeat every 16 iterations, okay? Each flip-flop will divide the frequency by 2. That's basically what happens here to the clock cycle. When the clock is up, this will not activate yet. And it will wait until this is activated again in the next interval. So when it goes up, it activates here. When it goes down, it deactivates, and when it goes up, the Q prime here activates and reversing the value here. Therefore, this Q becomes 0. Wow, I didn't explain that before. Okay. So for this solution, 4 flip-flops are needed following the 2 to the power of n. 1 over 2 to the power of n frequency division rule. Okay. Therefore, the timing will be 1/6 of the normal rate of change or frequency. Yeah, so this is basically it for my explanation for the current journal. If there's anything wrong or anything that I didn't explain correctly, because I'm doing it at around 6:20 p.m. a.m. 6:20 a.m. in the morning. Yeah, to create this assignment. Yeah. So thank you all, and I'll see you at the next time. See ya.